Okay, here's the reaction between sodium and water. There, and the chemical equation for that is shown on the next slide. So we have sodium and water. This generated hydrogen gas and sodium hydroxide, and some heat. Heat is an additional product. Heat, though, sometimes we'll write that on there, sometimes we'll leave it off. And so oftentimes when you'll see this reaction, it's just sodium solid plus H2O liquid. This is going to produce hydrogen gas plus sodium hydroxide aqueous. Okay, and the heat, it's optional whether you put that in or not. Well, this would be an example of an exothermic reaction. Exothermic reactions produce heat. Endothermic reactions consume heat. And so if this were an endothermic reaction, you'd see heat as a reactant rather than heat as a product. But heat as a product here, so it's exothermic. This reaction is not balanced. Is this where we left off last time? Or did we get farther than this? Beginning of chapter 8. Did we talk about these? Yeah. So this is it. All right. What we have to do, though, is we have to make sure this is balanced. Balanced means the atoms are just rearranged in a chemical reaction. They're rearranged to form new substances. So we have sodium here. Sodium ends up sodium hydroxide. So we have one sodium atom, one sodium atom. Over here we have two hydrogens, but over here we have 1, 2, 3 hydrogens all together. And so there's an additional hydrogen that appeared in the equation. Over here we have one oxygen, over there we have one oxygen. And so we would say that the hydrogens aren't balanced. That is, we have 2 hydrogens on the left, but 3 hydrogens on the right. We can't just add another hydrogen. So for example, if I want to just add another hydrogen atom to the left, is that something that's doable? No, it's not doable because when we look at the reaction here, it's just a chunk of sodium metal going in water. They're not adding atomic hydrogen to this. And so here I can't just add another hydrogen here. So I have to balance it by changing the coefficients. I can't change the subscript because let's make this an H3O. Now it's balanced, right? But what is H3O? You recognize that compound? No. So we can't do that. It's water we added. And so the way we change or balance this is by changing the coefficients that go in front here. And so one easy way of doing that is this. I have 3 hydrogens here. I need to cut it down by, so if I take half a hydrogen here, that gives me 1 hydrogen. So half an H2 gives me an H, and so that gives me 2 H's. Now there are 2 ways of interpreting this. Is it possible to have a half a molecule hydrogen? No. But if I have, let's say, a half dozen, so if I have a dozen sodiums and a dozen waters, then I need a half dozen H2s. Is it possible to have a half dozen? Yeah, I could have a half dozen. Or most often, this is taken, a dozen's too small, moles. So if I have a mole of sodium, a mole of water, I need a half a mole of hydrogen. And so that works. So fractions are okay. There's no problem. But sometimes they're not so convenient. And so what we'll do is we'll get rid of the fraction by multiplying the whole thing by 2. If we multiply the whole thing by 2, that'll give me 2 sodium solids plus 2 waters, 2 liquids. This is going to produce 2 times a half just gives me 1. So it gives me a full hydrogen and 2 sodium hydroxides. And so I can get rid of the fraction this way. If I get rid of the fraction this way, then let's make sure it's still balanced. 2 sodiums, and I get a total of 2 sodiums over here. 2 times 2 is 4 hydrogens. So that's 2 hydrogens plus the 2 from this. That's 4 hydrogens, and then 2 oxygens, 2 oxygens. So it's balanced. We have the same atoms before and after reaction, just rearranged into new products. Okay, these are common solid, liquid, gas, aqueous. So aqueous just means dissolved in water. So solid, liquid, gas, aqueous. In this case, we have all states of matter. The difference between liquid and aqueous, both are liquids, but aqueous is referring to a mixture, whereas liquid's referring to pure, like pure water. You know, that's typically what happens with those. So, as I said before, we don't add atoms like this. You know, if it's not there, we don't change the subscripts. That's basically what they're saying there. So balance the equation for the reaction between solid phosphorus pentachloride with liquid water. So phosphorus pentachloride. What's the formula for phosphorus pentachloride? It is PCl5. PCl5 is correct. It's a solid, so with the nest there. With liquid water. Well, liquid water is H2O. Liquid. Yielding. Yielding means, you know, to form or produce. This arrow means yield or produces. Aqueous solutions of phosphoric acid. What's the formula for phosphoric acid? And so if we have ic acid means the anion is what? Well, all anions are going to be negative. It means the anion is 8-ite or ide. 8-ite or ide. 8. Correct. And so if we have phosphoric acid, that means we must have phosphate. Phosphoric acid means we have phosphate. What's the formula for phosphate? Oh, probably want to look at the periodic table. It's probably the easiest way to get it. Just take a look at the periodic table. There's so many tabs open, I gotta get rid of them. When we're thinking about the 8s, what 2 did I ask you to memorize? Which 2 8s did I ask you to memorize off the periodic table? Silicate. Silicate is what? And? Not barium. Close. It begins with a B. Boron. Borate. What's borate's formula? Okay, what's silicate's formula? Yeah, okay, good. This should be automatic, you know, by now. How many weeks has it been? Has it been 1 week? More than 1 week talking about this? Or 1 week? If it's been 1 week, then you should have had 7 days. Each day you should be working at memorizing it. Borate is what? I mean, this should be like automatic, like motor memory. Like you're driving a car and you don't even know how you got to where you got to because it's all programmed in you already. And so like borate should already be programmed in your memory. What is it? It should be automatic. There should be no delay. Borate is this is not good. This is very, I mean, that's 7 days, and then memory fades. Day by day, it fades. Pretty soon, the final comes along, and you don't know what you're doing exactly. But before the final, we have the next exam. You should learn it by the final for sure. By the final, you should have seen it so many times that it really becomes automatic.
Those are only two things I asked you to memorize for the 8s off the periodic table: borate and silicate. Have you made an effort yet? I can understand if you made no effort, then obviously you aren't going to have it memorized, but you should start making an effort, just little by little every day. Borate is BO3. Oh, well, some people have made the effort, some people haven't memorized. Norlito, you had it memorized? No? Oh, I thought I heard somebody. Oh, okay. You have it memorized? What did you get? BO3 3 minus. It should be automatic. BO3 3 minus. BO3 3 minus. Carbonate. CO3 2 minus. Nitrate. NO3 minus. Fluorate. Chlorate. ClO3 minus. Bromate. Iodate. That's good. That's the way you want it. You want it like that. And then we go to silicate. What is silicate again? SiO4 4 minus. Phosphate. No. PO4 3 minus. Sulfate. SO4 2 minus. Do you see that? You're gonna have to train yourself to do that. You know, just it's not that difficult, I think, if you memorize these two. There's a pattern to it. And so it goes 4, 3, 2, then stays. Right? That's what we do. This goes 3, 2, 1. And so phosphate, you know, well, the other way that people memorize these is by flashcards, or you could try the books method. Did you look at the books method for memorizing these? It doesn't matter how you memorize it. I don't really care as long as you get it memorized. And so what you say is, you know, if you don't like this method, then pick a different method. You know, either rote memorization, or books method. That's the wrong chapter, I think. 7. Was it chapter 6? Nomenclature? Yeah, I guess it was 6. It was a couple weeks ago. So the way the book has you do it is they have you memorize the acids, the 5 acid names and formulas. So your book will have you memorize these, and then based off these, you can figure out the rest. I have you memorize, the advantage of the book is that you have the acids, the acid names as well as the anion. So either way is fine. There's no right way, no wrong way. Any way is fine. But the important thing is is if you don't feel strongly one way or the other, then just why not just try my method and then see. And so phosphoric acid. Phosphoric acid is phosphate. Phosphate is PO4 3 minus. You can see that because silicate is SiO4 4 minus. You write it down, you see the pattern. So we go from silicate to phosphate to sulfate. No, but we don't need that here. And so it's an acid. So if it's an acid, then what's the cation for acids? The cation is H+. So how many H pluses are we going to need? 3. And so phosphoric acid is H3PO4. So with go over here. So this makes phosphoric acid, H3PO4. And then hydrochloric acid. If we have hydro, ic, acid, what's the anion? I. Good. Anion is I. And so let's get rid of the hydro ic and we get chloride. The chloride, what's the formula for chloride? Cl minus. Chloride Cl minus. How many H pluses are we going to need? 1. And so hydrochloric acid is HCl. So we'll just add that here, plus HCl. All right, these last two are aqueous. So we write AQ here. AQ. So why don't you try to balance this one? When we balance it, the only thing we can change are the coefficients in the front here. So give that a shot. Get it? Got it? Got it? What did you guys get? Just curious. 1 4 1 5 1 4 1 5. All right, let's take a look here. Yeah, the way I would do it is I got 1 phosphorus here, then over here 1 phosphorus. That's good. The phosphorus are balanced, and we move on to chlorine. 5 chlorines here, but only 1 chlorine here. So you put 5 here, that's good. It's 5 chlorines. And then this gives us a total. We don't want to change these because that'll screw up phosphorus and chlorine. So there's 3 hydrogens here, plus 5 hydrogens is 8 hydrogens. So we'll get 4 here, that gives us 8 hydrogens. Hopefully the oxygen is balanced. It gives us 4 oxygens. We have 4 oxygens, so this is balanced. That's good.
Yeah.
Basically, interpreting what a couple ways to interpret the one is by molecule or by atom, or in other words, at the particulate level. And two is at the macroscopic level. So at the particulate level, we have two molecules of hydrogen reacting with a molecule of oxygen to form two molecules of water. The particulate level would look something like this. Two molecules of hydrogen reacting with one molecule of oxygen to give us two molecules of water. But when we're dealing at the macroscopic level, then we get the same ratios. So this is becoming more macroscopic, although it's still too small to see. 24 hydrogens is way too small to see. But anyway, this is 24 hydrogens, 1 oxygen, 2 waters. Normally we do mole, and so the two ways of visualizing this are by mole. Rather than 24, we have 2 moles. 2 moles, 1 mole yields 2 moles worth. And so a mole is 6.022 times 10 to the 23rd, because Avogadro's number is worth. 2 dozen, or 2 mole, actually 2 moles would be double that, 2 moles of water. And so either at the mole level or at the molecule level. And so, for example, we look at this. This is formation of 2 moles of water. If we just form 1 mole of water, then we need 1 H2 and a half an O2. It's not possible to have a half O2 molecule, but it's possible to have a half a mole of O2 or half a dozen of O2. So if we took 12 hydrogen, half a dozen O2s will form 12 water. Or if we take 1 mole of hydrogen and a half a mole of oxygen, will form a full mole of water. And so this macroscopic and particulate level. The other stuff I wouldn't pay attention to. Slide. Your book has different types of reactions that are discussed here. Like, for example, combination reactions, which have this kind of pattern here. And then there's something called decomposition reactions, the opposite pattern here. Single replacement reactions, double replacement reactions. And so it's all summarized at the end here. Combination, decomposition, single replacement, double replacement, plus others. And then your book goes on to precipitation reactions, neutralization reactions, et cetera, et cetera. And so these are just different types of reactions. These types are based on certain patterns of reactivity here. But if you think about all the chemical reactions that occur in nature, how many chemical reactions are there that occur in nature? Lots, probably. Trillions, would you say? Trillions and trillions of different kinds of chemical reactions? Maybe innumerable. How many reactions are going on right now in your body? Chemical reactions. Digesting food, getting energy, that kind of stuff. Lots. And so it depends on how you want to categorize things. I think our book has about 7 different categories of reactions. Now, the problem with that is the categories aren't comprehensive. And some of the categories have multiple types of reactions. For example, combination. Multiple types of combination reactions that occur. So I'm going to divide reactions into different set of categories. I mean, if you study, how many different kinds of plants and animals are there in the world? Do you know? Do you have an exact number? No. Lots and lots of different kinds of plants and animals. So what we do is we categorize those plants and animals into a smaller number of type. And we'll do the same thing with chemical reactions. There are lots and lots of chemical reactions, but we're going to categorize those into different types. And I'm going to use a different categorization scheme than the book. The book doesn't give you a comprehensive list. I'm going to give you a more comprehensive list. We're going to have 3 main types of reactions. The first type of reaction is redox. Do you know what redox stands for? Reduction and oxidation, or oxidation reduction. So an example of a redox reaction would be something like this sodium hydroxide reaction. We took sodium metal plus the water to a liquid to form H2 gas plus 2 sodium hydroxide aqueous. This is an example of a redox reaction. In a redox reaction, the charges change. It's not just the charge. For example, if I think about phosphate, what's the charge on phosphate? Yeah, the charge is PO4 3-. That's phosphate. But what we're looking at is not the charge. We're looking at something called the oxidation state. What was the oxidation state? Let's say the oxidation state is? I'm sorry? No, it's kind of related to it, but it's not the amount of oxygen. It's something else.
How many electrons required to strip away electrons or something?
The oxidation state is charged also. It's charged, but in a different sense. It was back in chapter 6, I think. It was charged in a different sense. And so the oxidation state is this. We pretend everything consists of monatomic ions. What it is it's a way to better understand the chemistry of what's happening, especially the redox chemistry. Phosphate doesn't consist of oxides, 4 oxides. And what's the phosphorus? If I have 4 oxides, what's the phosphorus got to be to add up to 3-? It's got to be +5, Roman numeral 5. And so +5 minus 8 gives us -3. The oxidation state is the charge on the individual atom, assuming that it's comprised of all single atom ions. The reason we do that is just for kind of bookkeeping and also to try to understand the properties of what's going on. And so the oxidation state would be the charge. Like, for example, what's the charge on sodium? Well, the normal charge is +1. It's sodium ion, but this is sodium metal. Sodium metal and sodium ion are 2 different things. Sodium metal, the charge is actually 0. And so I have 2 sodium atoms at 0 charge. This is like here. These are different ways of visualizing sodium, but this is the sodium lattice here. Each sodium atom in this lattice is 0 charge. So for example, here, if I have, let's say, 100 atoms here, then the whole charge on this is 0. Not plus 100. That's different than over here. And so if we go over here, this consists of what? This consists of sodium ions and hydroxide ions. Now take a look at the charge on sodium. What's the charge on sodium over here? It's plus. I have 2 of them, so I have these 2. So what happened to the sodium? The sodium went from 0 charge to plus. And so each sodium lost 1 electron, so minus 1 of E minus. And so I have 2 of those, so I lost 2 electrons altogether. All right, if I analyze hydroxide here, I pretend that hydroxide consists of the ions. And so I'll have oxide ions and hydrogen ions, like this. So if I take a hydrogen ion and an oxide ion, I'll make the hydroxide ion like that. Here. That's what I'll have. All right, so sodium ends up losing electrons here. All right, let's take a look at water here. If I look at water, I have 2 waters. And so if I pretend that water consists of ions, then water is going to have an oxide ion and 2 hydrogen ions, like that. That would make 1 water, and the second water would be just the same, like this. And so if I look at oxygen, did anything happen to oxygen? We went from oxygen 2 minus to oxygen 2 minus, nothing happened. And so what these are called is, the charge on this is 0, but when we do this, we're assuming that the species is made up of ions, monatomic ions, and the oxidation state is the charge on the atom. So the charge on the individual atoms. That's the oxidation state. And so oxidation state is also a charge. It's just the charge on the individual atom, not the whole species. And so the charge on the individual sodiums is 0. And so if I have 100 sodiums, the whole thing is going to be charged 0. If I have 100 waters, the whole thing is going to be charged 0, but each water has hydrogens at +1 and an oxygen at -2. So let's take a look at these. Over here, I form 2 hydroxides. And so I see the H+, nothing's happened to the H+. So I'm going from here, and then if I look at O2-, nothing's happened to the O2-, like here. And so there's no change. But I have 1 more species here, and I have hydrogen. What's the charge on hydrogen? Here. H2. Is it plus? Plus? If the charge on hydrogen is plus, then I have 2 of them, so it should be H2 with a 2+ charge. No, but it's H2 with a 0 charge. That means each hydrogen must be 0. And so these 2 hydrogens, nothing's changed. However, these 2 hydrogens, something's changed. When I look at these 2 hydrogens, the oxygen, nothing's changed. And so if I look at these 2 hydrogens, what happened? They went from plus to 0. In order to go from plus to 0, it has to gain a negative charge. And so we get a plus an electron, plus an electron. So the sodiums altogether lost 2 electrons, and these hydrogens in water gained those 2 electrons. And so this is an example of a redox. What species takes electrons? Is it the oxidizer or the reducer? It's the oxidizer. So when I look at this, this is water. The hydrogens in water were the oxidizer. The reducer is what loses the electrons. Sodium is the reducer. This water is the oxidizer. The other water, nothing happened to that, except it got rearranged. The atoms got rearranged. Nothing happened to in terms of losing electrons or gaining electrons. And so this is an example of a redox reaction. oxidizing reducer. Is this a redox reaction? Here. So what we do is, this is a molecular compound. This is a binary molecular compound, but we pretend as if it consists of ions, individual monatomic ions. And so even though this is a molecular compound, we do this so that we can gain better insight into the redox properties of this. And so let's pretend this consists of ions. What ions would this consist of? It consists of 5 chloride ions. What's the charge on chloride? Chloride would be -1 charge. And then 1 phosphorus. What would the charge on phosphorus be? It's got to be +5 or Roman numeral 5. That's because PCl5 is neutral. So if I have 5 positive charges and 5 negative charges, they're going to add up to 0. That's what's happening here. And then I have 4 waters. Each water consists of 2 hydrogens and an oxygen. What are the oxidation states here? Hydrogens are going to be +1. Oxygen is going to be, let's call it 2-. So I got 4 of those. Let's go ahead and put those in here. Water doesn't consist of ions. Water is a molecular compound, but we do this so we can understand redox reactions a little better. All right, H3PO4. H3PO4 consists of 3 H pluses and a phosphate. And so what we're going to do is we're going to break down the phosphate and pretend it consists of ions. So what ions would it consist of? It would consist of 4 oxides and a phosphorus. What would the phosphorus be? It's got to be +5. And then finally HCl. We have 5 HCl's, so we're going to have 5 H pluses and 5 Cl minuses. Now, the reason we break it down like this, is to see what's happening with the charges and what's happening with the electrons. In a redox reaction, electrons are gained or lost. For example, the oxidizer, do oxidizers take electrons or do oxidizers give up electrons? Take. Oxidizers take electrons. So, did anybody take electrons in this? Did anybody give up electrons in this? No. In fact, if you look at all the oxidation states, did anything change? Nothing changed. Therefore, this is not redox. There's no oxidizer, which is going to take electrons. There are no reducers, which are going to lose. This is not redox. If it's not redox, what kind of reaction is it? Well, let's look at our list of reactions. Is it a combination? No. Is it a decomposition? No. Is it a single replacement? No. Is it a double replacement? No, it's not a double replacement either. Although it might seem like it, it's not. So it's none of the above. Well, that's the problem. The problem is our list is not comprehensive. But anyway, this turns out to be another type of reaction, not a redox. This turns out to be an acid-base reaction. Acid-base. And it's a specific type of acid-base. It's called a Lewis acid-base reaction. We'll talk more about these types of reactions later, but all Lewis acid-base reactions share something in common. Well, since we're on the topic of balancing reactions, look, some more. Acid-base reactions, there are two subtypes that we look at. There's something called the Bronsted acid-base reaction. And a Bronsted acid-base reaction would be something like this. It'd be like ammonia plus HCl. NH3 is ammonia, HCl is hydrochloric acid. But we're going to put these in the gaseous phase. When we do this one, this makes ammonium chloride. Ammonium chloride. Ammonium chloride is solid. Both of these are gases here. Hey, you know what that looks like? That looks like a combination reaction, doesn't it? A plus B combined together. It is. This is like a combination reaction. Here. But the problem with combination, as they describe it here, is there are many different kinds of combination reactions. There's redox combination reactions, acid-base combination reactions, and there's one more type of combination reactions. But this would be Bronsted acid-base. And then there's something called Lewis acid-base reaction. Lewis acid-base reaction would be something like BF3 plus ammonium. This is going to produce BF3NH3. This is one compound here. It's kind of a weird compound, BF3NH3. But this looks like a combination reaction, doesn't it? You're combining two things to form one thing. Another type of reaction is called the metathesis reaction. Let me give you an example of a metathesis reaction. One example is if I take silver ions, which has a positive charge, plus chloride ions, which is a negative charge, I'll make this, silver chloride solid. So if I take aqueous silver ions and aqueous chloride ions, I can make silver chloride. I'll talk about the ions, aqueous ions, later, but there's got to be some things. So this also looks like a combination reaction. And so we have combination reactions that are redox, combination reactions that are metathesis, and combination reactions that are acid-base. Both Bronsted and Lewis. So the only thing that combination reactions have in common are that you're taking one thing, combining it with another to form one thing. It's an A plus B yields a C. But it's not a very useful way to categorize things because there's so many different kinds of combination reactions. So rather than looking at that, we'll look at redox reactions, acid-base reactions, and metathesis reactions. Number 3 here. There's certain kinds of metathesis reactions. So another example of this is, where do I get aqueous silver ions? I can get aqueous silver ions from something like this, AgNO3. Do you know what this is called? AgNO3. Silver nitrate, good. And NaCl, which is called sodium chloride. And this is going to be AgCl solid plus NaNO3. This is what we call a precipitation reaction because we're forming a solid. The aqueous species are liquids, liquid solutions. both of these are the same. So the reason I have this categorization scheme is because of this. All redox reactions share something in common. All redox reactions will show change in the what? All redox reactions are going to show a change in the oxidation state. Do all combination reactions show change in oxidation state? No. Some of them do, yes, but a lot of them don't. And so what we want is we want something where we have something more in common than just a red ball and a green ball coming together. And so I'm gonna drop their classification scheme and use a different alternate classification scheme. There's something that all Bronsted acid-base reactions have in common. There's something that all Lewis acid-base reactions have in common. And there's something that all metathesis reactions have in common. And that's how we can recognize these types of reactions. There are three main types of reactions, which we'll be looking at. And so I'm not exactly going to follow the book. And so let's take a look at their combination reaction here that they give. This is what they say. Combination reactions, known as synthesis reactions. Two or more substances combine to form a single product. Okay. And so let's take A plus X yields AX. Write the equation for the combination of solid aluminum and gaseous oxygen to form solid aluminum oxide. All right, so what is solid aluminum? What's the formula for that? A, G, Al. Al, what's the charge on Al? Al's a 3+. But this is the element, the solid aluminum. Solid aluminum element consists of a lattice that looks like this. This is the lattice for aluminum, nickel, silver, copper, and gold. And so we put aluminum atoms here. If the aluminum atoms are 3+, this would be 3+, 3+. So 3 plus 3 plus 6 plus 9 plus 12 plus 15 plus 18, 21, 24, 27, 30, 33, 36, 39, 42, 42 positive charges in this tiny crystal. And so this is Al. Is it plus 42? If I have a bigger crystal, it's going to be even more positive. And there's no anion here, so there's nothing balancing it out. So it depends on how many aluminums I have there. If I have 1 million aluminums, then it's 3 million plus 3 million. Should I put it? If I have 1 million aluminum atoms, then the charge is plus 3 million. Yes? No, it's because this is different. This is not the ion, this is the element. The ion forms in compounds of aluminum. And so when we're looking at the aluminum, a metal alone, all these are 0. In fact, we know one chemical property of metals, and what chemical property is that? Metals tend to be reducers or tend to be oxidizers? Reducers, because metals tend to give up electrons. They're reducers. And so this is a metal, it's got to have some electrons to give up. And so we're going to have 0 as the charge here. It's just Al solid. Plus oxygen. Now the normal charge on oxygen is 2 minus. And so I have 2 oxygens there, so I should write this as O2, and each oxygen is 2 minus. So if I take those 2 and combine it to form an O2, then the charge is going to be 4 minus. So oxygen is O2 4 minus. Is that correct? The oxygen we're breathing right now is O2 4 minus. No, that's not correct, because we're dealing with the element. You know what oxygen, the oxygen we're breathing right now, is it an oxidizer or is it a reducer? Well, oxygen is an oxidizer. We live in an oxidizing atmosphere. There's oxygen present. And what oxygen wants to do is it wants to take electrons, but right now it still has not taken any electrons. And so this is oxygen in the zero charge. It's neutral. So the elements in elemental form, like solid aluminum, gaseous oxygen, are neutral. There's two oxygens, but each oxygen is zero charge. So I combine them together, I'll get O2 with no charge. And this is going to form aluminum oxide. Well, aluminum oxide is a compound, ionic compound. So aluminum ions are 3+, oxide ions are 2-. And so how many of each of the ions will I need to balance out the charge? I'll need 2 aluminums and how many oxides? 3. And so this gives me a total charge of +6, total charge of -6. So it's a nice balance. So it'll just be Al2O3. Okay, this is solid. So what's happened here? Well, first let's balance it. Over here I have 1 aluminum. Here I have 2 aluminums. So what should I do? Change this to a 2. Over here I have 2 oxygens. Over here I have 3 oxygens. So what should I do? Well, here's a trick that we can do. I have 2. I have 3. So if I multiply this by 3 halves, the 2's cancel. That gives me 3. But it also gives me a fraction. Sometimes I'm okay with the fraction. In Chem 1A, you're going to be okay with the fraction because in order to form 1 mole of aluminum oxide, we have to have a fractional amount of oxygen. If I double everything, that's one way to get rid of the fraction. I double it, so that turns into 4. And if I double this, that turns into 3 O2s. And if I double this, we'll just get 2 Al2O3. So sometimes what we want is we want to form per mole. Sometimes we want to form per 2 moles. You know, how much does it take to form a mole? Well, in order to form 2 moles, we've got to double everything. And so either of these equations is okay. Let's take a look at the second equation there. We look at it at the particulate level. If we look at it at the particulate level, we have 4 aluminums. The charge on the aluminums is what? 0. Okay, over on the right, how many aluminums do we have? We have 4 aluminums, but the charge is not 0. The charge is, we call 3+. And so that means each aluminum had to lose how many electrons? Yeah, -3 electrons, each one. -3 electrons. -3 electrons. -3 electrons. Each aluminum lost 3 electrons, so that gives us a total of -12 electrons total. So who took those electrons? Who took the electrons? The oxidizer took the electrons. What's the oxidizer? Oxygen. And so we have 3 O2s. 3 O2s is 6 oxygens. Each oxygen is 0, 4, 5, 6. And then over on the right, we have 6 oxides. Oxides. So oxygen goes from 0 to -2. That means it must have gained 2 negative charges. That means it must have gained 2 electrons. Plus 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 2 electrons. So in this case, the reducer lost a total of 12 electrons, and the oxidizer gained a total of 12 electrons. Plus 12 electrons total. And so this would be an example of a redox combination reaction. Or an element plus element combination reaction. Okay, let's take a break here and then do this after.